When an aromatic ring possesses substituents, those substituents affect the course of an EAS reaction in two important ways. One is that they accelerate or decelerate the reaction, and the second is that they will impact its regiochemical outcome. Dealing with the first part of this, the rate of reaction, substituents that accelerate EAS reactions are known as activating groups. On the other hand, those that decelerate reactions are known as deactivating groups. In regard to the second component, regiochemical outcome, substituents will either direct an EAS reaction to the ortho and para positions, or they will direct it to the meta position. Over the course of a few examples in a series of videos, we'll consider why particular substituents exert the effects that they do, and then we'll generalize these effects, showing how you can predict the impact that a substituent will have on an EAS reaction. Let's begin with the chlorination of toluene. This reaction in the laboratory happens to be faster than the chlorination of benzene, which shows us that the methyl group is an activating group. Alkyl groups are electron donating, so the ring is more electron rich as a result of the presence of its methyl substituent. In EAS reactions, the benzene ring always behaves as a nucleophile. The more electron-rich a nucleophile is, the more effective it will be. And this is the reason why the methyl group accelerates the rate of this particular reaction. Its electron donation makes the ring a better nucleophile, and a better nucleophile reacts more rapidly. The predominant products of this reaction are the ortho and para isomers. The meta isomer is a very minor product. To understand why we see direction of EAS to the ortho and para positions, we need to examine the mechanism. This transformation begins with a Lewis acid-base reaction between chlorine and iron trichloride. The next step is the attack of toluene on the electrophilic terminal chlorine of the Lewis acid-base adduct. Now this could occur so as to place the halogen ortho, meta, or para to the methyl group. It turns out that the ortho and para pathways are electronically equivalent to one another, so we're going to look at just one of the two. The pathway shown here places the chlorine ortho to the methyl group. There are two additional resonance forms that stabilize the carbocation intermediate. Note that one of them contains a tertiary carbocation, while the other two are secondary. And of course, the tertiary carbocation enjoys further stabilization due to the presence of the electron-donating methyl group. Lastly, the loss of a proton to chloride generates the ortho product. And the para product is produced through an analogous mechanism. You should prove that to yourself. It's a good idea to pause the video at this stage, draw the mechanism for the para pathway, and convince yourself that the sigma complex has similar resonance structures in that one of them will contain a tertiary cation while the other two are secondary cations. Now, for comparison's sake, let's consider the meta pathway. Doing so will help us to understand why the meta product is not formed in a significant quantity. Once again, the initial attack of the ring is on the Lewis acid-base adduct, and it produces a carbocation intermediate. When we draw the resonance forms for this sigma complex, we see that all three are secondary carbocations. And this explains why the meta pathway is not as desirable as the ortho and para pathways. Recall that both the ortho and para pathways had at least one resonance contributor to the hybrid that was a tertiary carbocation. So in summary, we have determined that the ortho and para pathways will be preferred over the meta pathway. But now we have to take a look at ortho versus para. Which of the two is predominant? In this specific case, the ortho product is the major product. And the reason is simply statistical. There are two ortho positions, the two carbons flanking the methyl group. But there's only one para position. Therefore, it is simply twice as likely that substitution will occur at the ortho position. However, with alkyl groups larger than methyl, the reverse is true. Para predominates, and it is the major product. And the reason is that as the substituent grows larger, steric hindrance disfavors attack at the ortho position. And it's the sterically uncongested para position that becomes our preferred location for substitution. The next video in this series will continue our discussion of the effect of substituents on EAS reaction. We'll consider substituents that are activating ortho-para directors because of their direct involvement in resonance.